Привет. Sorry. Uh, Good morning.
Здравствуйте.
Yes, we can speak in Russian this 8 minutes, yes, but I still prefer English. Maybe some foreigner will just switch to our conference. Um, h- Marina, how are the things going? So um, for Thursday, so you will let us into the conference, and then you will go and we'll end it ourselves.
Um,
Or maybe
you
we'll,
will start and finish the conference yourself,
okay,
but it will be recorded automatically.
okay, very good.
Mhm.
Okay, so you will just send me the link, yes?
And the slides if you need them.
No, no, the slides, there will be only philosophy, so maybe I will find the slides on the internet. It's, well, I will see. I don't
Okay.
remember how I did this last lecture last year. Maybe have some slides already with me. So, um, and yes, and tomorrow there will be our first attempt of an exam. And so there will be a lot of presentations. I think, uh, well, for everybody, I can remind you that there is a list which was prepared by Ekaterina Skitchenko. Yes,
Yes.
okay. Well, what else? How is the weather? How is the all general mood?
um, it looks fine. I haven't been outside, but it looks nice. Very calm.
Calm, yes. No snow and no rain. And it seems that it is some maybe 1 or 2 degrees below zero.
Yes, maybe one or two.
Okay, very good. So I've checked a lot of essays. I think more than 100 uh, first essays and more than 100 second essays. So I think I've checked about 250. Some people seem to drop out. I don't know whether they will reappear, but maybe, but this is not a large percent. I think maybe 5 or 10 people.
Do you mean drop from Zoom or?
No, no, they didn't drop from Zoom. They just didn't deliver or load the essays. Not
Oh, it's fine.
neither
It
the first
happens.
nor the second. So I don't know what is. Maybe some of them decided that they will do. This is the notion I was told to drop out. Um, I think it is possible. So they, um, well, this is normal. It happened every year. So some 5 or 6 people who, or 10 maybe, who enlisted in my course just decided to discontinue. Um, well, this is normal. I'm very happy with the essays. I think they're most people did their best. The English is very good. Comparing with the previous years, it's seems that the English becomes better and better. So I can say that perhaps the learning abilities of our educators are growing. I have no other explanation. So maybe in Russian school now we have better quality of English teaching. Um, well, what else can I say as an introduction? Um, well, that today is um, the ninth lecture, and on Thursday this will be the last lecture. So we have to make it very concise. So I apologize for the fact that I cannot cover all the subjects. Today we'll speak about science in the 20th century. So I will highlight only the most important events, maybe from the philosophical point of view, rather than I will maybe skip some technical details. Well, I think it will go because 8 lectures have already passed and nothing terrible happened. So this is an inductive method of Bacon that perhaps we can hope that the 9th lecture will also go smoothly. But Karl Popper or David Hume would say that we can't be certain about that because this kind of induction is not valid for, say, certain conclusions. Probably, we can say probably it will end in a, well, properly without any accidents, but who knows? So let's hope and let's continue. If there are some questions on just the procedure of the exam, well, I can say, well, I think about 10 people have enlisted for tomorrow. So we'll see how we'll manage to hear 10 presentations in 3 hours. But if, well, including some maybe pauses or just a little rest, I think we'll have 10 to 15 minutes for every student. I mean, tomorrow. Maybe there will be more sort of hectic days with more students, and so we'll have less time for everyone. But we'll see how it goes. I hope that it will be as usual. Now it seems that it's 9 hours, yes, already. So Marina, can you give us the slides? So this slide with Chesterton, the return of Don Quixote, or Don Quixote, as they say.
Okay, just a second.
This is a interesting novel. It's not connected with the science, but the image I like very much. I mean, the return of Don Quixote. I will, yes, here. You know, Gilbert Keith Chesterton is a famous detective story writer, but also I think a journalist and the original thinker who lived in the end of the 19th and the beginning and the first half of the 20th century. A gentleman and I think a very intelligent and well man. He speaks about the return of, say, eternal values, which he associates somehow with the medieval period, being, I think, the last of the Romantics. Well, what is the return of Don Quixote? So Don Quixote is the last figure of the so-called Middle Age Renaissance period. So he's the symbol of nobleness, but also of an outdated person, that a person who cannot accustom to the environment because the things have changed. We have the similar subject in a novel or play by Michael Bulgakov. Ivan Vasilievich changes his profession. So it also can be renamed as the return of Ivan Vasilievich, or Ivan the Terrible. So, but if we say the return of Ivan the Terrible, that would sound very scary. So the return of Don Quixote is less scary, you know. Well, why do I use this metaphor? I will just explain. I use this metaphor in relation to Mendel's discoveries on pea seeds. Yes, then, Marina, you can just move to a slide where this Bateson book about Mendel. There's a slide uh, uh, no, uh, this not. Yes, here. This is William Bateson, a famous English geneticist, and he was one of the main figures in sort of reestablishing the reputation of a sort of mm, uh, mm, of Gregor Mendel, whose discoveries were not properly noticed in the year when they were published, or years. Well, he published them in 1860s. And here is in this book, there are the English translations of these articles of Mendel, which were published in Brno, in the periodical, which was very obscure at that time. And Mendel sent his articles to Charles Darwin, but perhaps Charles Darwin thought that there's nothing interesting there, and he didn't even read them, which can be seen that at that time the articles were published in this way that one should use a knife in order to sort of read them, cut them the pages with a knife. Well, now it is of course only old people know about that, but at that time it was the way the prints were sent. So, well, it was not cut. It remained, so we can see that it was not open. So Darwin couldn't open all the letters or read all the letters and articles that were sent to him. And so unfortunately, Darwin didn't take notice of Mendel's discoveries. Also, other biologists were very skeptical at first. And why? Because if we just use this metaphor of the return of Don Quixote, then we can say that here in his discoveries, there was a return of Aristotle. You remember the four elements of Aristotle: um, air, air, fire, water, and earth. So four elements built of two opposed qualities, so or one or two pairs of opposed qualities. So, for example, there is a combination of, say, and the qualities were hot and cold, and um, wet and dry. So you remember, if we take wet and cold, we'll receive water. So now we have these two combinations of two opposite qualities. So smooth and rough, mm, like the surface of the moon. You remember in these discussions started by Galileo, whether the surface of the moon is rough or smooth. Well, they can say wrinkled also about the seeds. So I apologize with the biologists who are, I think, listening to me, that they perhaps are accustomed to more certain terms or precise terms when speaking about genetics. So maybe the word rough applied to seeds will seem strange for them. Maybe they will prefer wrinkled or something like that. But here's Mendel's principles of heredity rendered into English by William Bateson. So there we can find exact terms. Well, everything can be now checked and verified or falsified. Okay, so wrinkledness, we'll say, and smoothness are opposite qualities, okay? Like, say, dry and hot with Aristotle. This is an analogy, but that's how it goes. Now we have also yellow color and green color. Well, they are not, of course, opposites. We cannot say that yellow is opposite to green, but this is two pair of qualities. And out of these two pairs of qualities, yellow, green, wrinkled, and smooth, we can form four variants, say green and wrinkled, green and smooth, white and, oh, I'm sorry, yellow and wrinkled, and yellow and smooth. So here we have this return of Aristotelian model. Well, in another disguise, sort of, or disguised just in another clothes, but the same idea remains at the core. That's why I call it the return of Aristotle, sort of Aristotle's, and perhaps that was perhaps the most challenging thing in Mendel. Well, also we can say that Mendel was a monk and a priest, and he lived in Austro-Hungary, which was regarded by England as a backward state, you know, because it was an empire. So this was like partly medieval. So, well, for England was considered progressive, and Germany also, and France. And the Austro-Hungarian Empire seemed a little bit backward. So this was the first, I think, cause that Mendel remained sort of unlistened to. The second, that he was a priest and a monk and had no reputation among scientists. And his article was published in an obscure periodical, published in Brno or Brünn, it was at that time called in a German manner, and also published in German, not in English, not in French, not in Latin. And the last was this Aristotelian formalism, which seemed a little bit childish. Okay, so we have already parted with Aristotle long before, with Galileo or with Descartes, with Newton, with this, we called it scientific revolution of the 17th century. So what's use to sort of to return to these Aristotelian formalisms? Well, this is how it goes, you see. So that's why Mendel was not properly understood, and he died in obscurity. Nobody, when he died, only his monks of his monastery sort of mourned about his death, but biologists just didn't care. If you take, for example, the encyclopedia of Brockhaus in Russian, there was a famous encyclopedia published, Brockhaus Ephron, it's called. It was published in Russia at the turn of at the end of the 19th century. There's no article on Mendel. You cannot find that article. Well, this is the first thing that happened with Mendel. So we could have hoped that with the publication of Bateson and with the rediscovery of his laws made by other geneticists at the end of the 19th and the beginning of the 20th century, this story will happily end, and Mendel's like reputation will be reestablished firmly, and that's what perhaps Bateson thought. But history has some surprises for that. It happened that in the Soviet Union, the history of genetics will have some unexpected turns, sort of. Bateson is connected with our famous Russian and Soviet also geneticist Nikolai Vavilov. So Marina, can you show us the portrait of Nikolai Vavilov? It's somewhere there in the slides. Yes, here's Nikolai Vavilov, and here's Nikolai Timofeev Rysovsky, two famous Russian and we can say Soviet geneticists, because their scientific career coincided with the so-called Soviet period. I mean, Soviet period, which started with the October Revolution of 1917 and ended with the Gorbachev's perestroika or with the so-called August Revolution of 1991. Well, you can, well, more or less say that this is the Soviet period, okay? Uh, at the end of this period, the Communist Party of the Soviet Union was outlawed. In its stead, there appeared the Communist Party of Russian Federation, which still exists, but it is not a ruling party, it's in opposition. And well, but well, I think in many countries, in Venezuela, for example, if Javier is present, he can confirm that in Venezuela you also have communists. I mean,
Yes, right now we have,
yes, and
unfortunately.
I think we have communists in India or in Italy or in China. So communist ideology is present. And in China, they are still ruling. I mean, the communists, the ruling party. But here we say that in Russia, there was a period which ended in, we can say, 1991. So returning to Nikolai Vavilov. Nikolai Vavilov, at first, Soviet power, we can say, or Soviet authorities were benevolent towards scientists, well, towards physicists and also biologists. Yeah, I can give you some examples. For example, well, Alexander Friedman, who was the one of the key figures in formulating this theory of expanding universe. He showed that the Einstein's equations are not stable and sort of uh, uh, there can be a solution which will lead to expanding universe. So he published his works in 1920, his first article on that theme in 1922. And he traveled abroad so he could meet, I didn't know whether he met with Einstein himself, but he was allowed to travel abroad in the early 20s. Unfortunately, he died from typhus in 1925, but of course this was an accident, so nobody sort of he found no persecutions at that time. I mean, Alexander Friedman. So and he was also like Mendel. His discovery was not properly esteemed, first of all, by Einstein, who later regretted about that and said that it was this not understanding the significance of Friedman's work was the biggest blunder of my life. Well, this is one example that Soviet authorities allowed scientists to travel abroad. The second example is Landau, who was also allowed to travel, and even he met with Einstein and tried unsuccessfully to convince Einstein in the validity of Copenhagen interpretation of quantum mechanics. He stayed also with Niels Bohr in Copenhagen. Here you can see on this slide how Landau met Niels Bohr in I think in 1861 when Niels on 1961 when Niels Bohr arrived to Moscow and visited Moscow University. So Landau was allowed to travel in the 20s, and also Georgy Gamov was also allowed to travel and to publish his works in German periodicals, scientific periodicals. So in 1928 appeared a famous article by Georgy Gamov on tunneling. So he explained the alpha decay by means of solving Schrodinger's equation and showing that Schrodinger equations allows this classically prohibited sort of process of tunneling, okay, or just going under a potential barrier which is unsurmountable in classical mechanics. Okay, well, that's how Russians and also the same was with geneticists. So Vavilov was allowed to travel to England and to work with Bateson. So Bateson and Vavilov were friends like Niels Bohr and Lev Landau. But unfortunately, we cannot find this photo of Nikolai Vavilov receiving Bateson in the Soviet Union, because genetics was the first victim of so-called revision, Marxist revision of science. Well, it all started with the book of Vladimir Ilyich Lenin. Yeah, I know that people just shudder when I mention this surname, Lenin, but I will explain to you that it's used not only by me, but for example, by such an important historian and philosopher of science as Paul Feyerabend, of whom we'll speak, I think, on Thursday. So I'm not alone. Feyerabend said that Lenin was a thinker of first class thinker. This is a citation. Well, I'm not an admirer of Lenin by no means, and his politics was very cruel. But as a philosopher, he was just taking a position in this discussion about so-called second positivism and their objective reality of the world. Okay, so this work of Lenin which was named Materialism and Empirical-Criticism. I will just write it because it's difficult to pronounce. The people of my generation learned it almost by heart. This work of Lenin. So for me, it's not difficult to pronounce. It's empirium. Well, we know this, what is empiricism. Now it is empirical-criticism. Empirical-criticism. Criticism. Well, criticism. Well, no, here is C. Okay, so Marxism and empirical criticism. Oh, no, not Marxism, I'm sorry. Materialism. Materialism, that means that I haven't slept well. Materialism and empirical criticism. Well, of course, it can be also called Marxism and empirical criticism, but it's really it's called materialism and empirical criticism. Empirical criticism. Well, maybe I made this mistake on purpose, or maybe it has some Freudian interpretation. We'll speak about Freud also, maybe. Materialism and empirical criticism. Empirical criticism. Maybe empiric. No. Maybe here's why. No. No, I think it's okay. Well, please check me because I'm not in a proper form today. I didn't sleep well, so I may make curious mistakes. So materialism and empirical criticism. Here I made another mistake. Empirical criticism, I think, well, chat doesn't allow us to sort of to edit our posts, so they are all wrong. But well, you can find this book in Wikipedia article and look at it. So it was published in 1908. At that time, there was a big discussion among physicists. Yes, thank you, Noreen. Yes, okay. So at this at this time in the beginning of the 20th century, there was a big discussion about whether what we observe is real, or whether we should sort of regard the world as unknowable, and only what we have, our scientific theories, are only models which can sort of save the phenomena, so we cannot speak about objective reality as such. We can speak only about our observations and our experiments. This is the like the gist of the so-called second positivism. You remember we spoke during our last lecture about Auguste Comte and his theory of three stages. So Auguste Comte, together with Mill and Spencer, is the representative of the so-called first positivism, or simply positivism. And because, of course, Auguste Comte didn't call his philosophy first positivism, he just called it positivism. But then there appeared another generation of positivists, for example, Ernst Mach, a famous physicist, you know, the cone of Mach, Ernst Mach, Henri Poincaré, and Pierre Duhem. So they are also Avenarius. They are all representatives of the so-called second positivism, and it is connected with empirical criticism, or criticism of our interpretation of our experiments. So, well, Lenin took a stand in favor of the so-called objective reality of matter, of atoms, of properties. So he didn't. Why was it important for Lenin, this objectivity? Because, or absolute truth, as he called it, or objective truth, objective reality, because he had plans to change the whole world, and first of all Russia. So he planned already many painful reforms and persecutions of, as he called, obsolete or outdated institutions, like, for example, the Orthodox Church, or capitalism as such. So he planned requisitions, nationalization of property, division of church from state, and persecution of those priests or those officers who were against this his communist party. And so he was very brutal in his politics, and he could appeal to masses and sort of reconcile himself with his own conscience only if he thought that he was objectively true, that his ideology was absolute truth, and the ideology of his opponents was false. But second positivists like Ernst Mach and well, Henri Poincaré and others, they didn't regard their assertions as absolute. They say, well, our experiments show this or that. Well, if we say come to the question of the existence of God, the second positivists took agnostic position, that we don't know whether God exists objectively or only in our imagination, because we have no experiment, no procedure to observe God. So God is a thing in himself, okay, according to Kant. So we cannot observe him. So we cannot say whether he exists or he doesn't exist. So if Lenin would take such a stand, then how could he demand the sort of the persecution of the church? Because the persecution of the church can be sanctioned only on the supposition that God objectively does not exist, and it's all invention or trickery of the priesthood, and that we should just establish, well, we should follow the true way, the true sort of picture of the world, in which there's no place for God or religion, whether Muslim or Christian or Jewish or any. So this all fantasy. Objectively, you understand? Objectively, it's bad. Objectively, it's erroneous. So we should just educate, say, young people in sort of materialism and atheism. We should we will not allow, say, young people to visit the church. We will persecute those priests who will speak openly against communism. So all this, well, then we'll just introduce other harsh measures like collectivization of farms and exiling of those peasants who used hired labor, for example. They were called kulaki. Kulak is a fist in Russian, but maybe I think it's now known. So this harsh politics also, but it was not conducted by Lenin, it was conducted by Stalin, but the ideology was the same with Stalin also, that there is some objective reality, objective truth of Marxism or materialism, and all should be interpreted in the light of the one absolute and say infallible teaching of Marx and Engels. Okay, after Lenin died, he was added to this list, so there was an infallible teaching of Marx, Engels, and Lenin. Okay, and the living authority or Lenin today was Joseph Stalin. Okay, that's how it happened. But it was all at the beginning when Lenin wrote this book. Nobody just cared about Lenin, and nobody noticed this book and say, well, Ernst Mach underwent a stroke, so he was not able perhaps to follow the literature, so he didn't react on Lenin because he wasn't just didn't feel well. But others like Guillaume and Poincaré, who just didn't notice this criticism, especially if we consider that this book was published in Russian, not in German, not in French, not in English, and was not, of course, translated immediately in European languages. Now I think we have the translation. I've seen the English translation, but I think there is also a Spanish translation and maybe others. So things drastically changed in 1917 when Lenin seized power, and now volens nolens, so people had to admit that he's the leader of a powerful state, okay, which just, you know, Russia is very, still is, contains 1/6 of all Earth's dry territory, okay, dry land. So, well, and Lenin was victorious in the so-called Civil War, so he managed to chase away or banish all his opponents from the territory of the Soviet Union. And so, well, this was a reality. So at first, now returning to science, and we'll see that at first scientists were treated benevolently by Lenin and by communists. They were allowed to travel abroad. The universities were not closed. There was financial assistance to scientists, even taking into consideration that after the Civil War, there was a terrible famine and also what we call in Russian razrucha, which we can say as just crisis, economic crisis. And nevertheless, the money was found for science and for travels of such people as Alexander Friedman, Georgy Gamov, Lev Landau, and Nikolai Vavilov, and also Timofey Frissovsky. Marina, let's return to this slide where Vavilov is on the left side, and Nikolai Timofeev Rysovsky is on the right side. Because Timofeev Rysovsky is perhaps less known than Vavilov. So Nikolai Timofeev Rysovsky was sent to Berlin in like a scientific, well, we say командировка, but maybe in English, like it will be he was sort of staying there in frames of scientific exchange, you know, as for example, as you are staying in Moscow, sort of invited professor, sort of, or invited scientists. So he worked in Berlin in the laboratory, and he was a geneticist like Nikolai Vavilov. And at first there was no symptoms that genetics will not fit in Soviet ideology. But already in the 20s, just another thing. So what happened? That Nikolai Timofeev Rysovsky didn't want to return to the Soviet Union. And after the end of his stay, he just disobeyed Soviet authorities and stayed in Berlin. And in Berlin, you know, in 1933, Hitler came to power. So now this, Timofey Rysovsky was sort of working with Hitler, sort of he was a collaborator of the Nazi Germany. So this was a crime. So he was regarded as a criminal, okay? Also, Georgy Gamov also left Russia and didn't want to return. So there were two so-called non-returners, okay? In Russian, we say невозвращенцы, okay? So Georgy Gamov and Nikolai Timofeev Rysovsky. Maybe there were others. We don't take the, say, the domain of culture. Otherwise, we can multiply to infinity the cases of when prominent people didn't want to return to the Soviet Union and stay abroad. Like, for example, actor Mikhail Chekhov, the nephew of this famous writer Anton Chekhov. Well, now we can say that perhaps these two circumstances sort of were changed, well, provoked this change of attitude towards scientists from benevolence to suspicion. So now scientists were regarded with suspicion as potential enemies of the state. And so their destinies drastically changed. For example, a very important, but Young, unfortunately, he didn't make much in science, but Bronstein, he was, his surname was Bronstein, and he was married to the daughter of a famous Russian writer, Kornei Chukovsky. He was married to Lydia Chukovskaya, Lydia Korneevna. And he was arrested and shot, executed, a physicist, a friend of Landau. Landau himself was put to prison, but thanks to Peter Kapitsa, who applied, and Niels Bohr, who sent direct letters to Stalin, he was released after 1 year of internment in prison. Landau. So he was somehow miraculously saved. And that's why we can see this fateful or important photo of Landau and Niels Bohr already in the beginning of the 60s. He was just receiving Niels Bohr as a guest of the Soviet Union in Moscow University. But Nikolai Vavilov also was arrested in the 30s, and not perhaps Stalin wanted to maybe liberate him from prison, and but he died in prison out of bad nourishment, led to certain disease like pellagra, and he couldn't survive because of these terrible conditions in prison. So he died of hunger, we can say. And his brother, well, maybe Stalin felt some remorse of conscience, and he made his brother, Sergei Vavilov, a physicist, the chairman of Russian Academy of Sciences, or Soviet Academy of Sciences, as it was called at that time. Well, it's terrible that brother, these brothers loved each other very much, and Sergei Vavilov had to start all his speeches before the academy with sort of some compliments, we can say, towards Stalin and his infallible guidance of Russian science, and that he was a coryphée of all sciences. You know, if we read his addresses, I mean Sergei Vavilov's addresses, to just take them, they are all of course published. So if we take them, we can see that he was like a president of the Stalin's Academy. Okay, there was an article published in with this title, President of Stalin's Academy. But under all this surface was a deep wound, which we can see from private letters of Sergei Vavilov, now published. So here we see, and now with Nikolai Timofeev-Rissovsky, you know that in 1939 the Second World War started, and in 1941 Germany declared war to Soviet Union. So there was 4 years of fierce fighting, after which Russians were in Berlin. So Hitler was defeated and committed suicide, and Nikolai Timofeev-Rissovsky was arrested in Berlin by Russian police, secret police, and sent to labor camp. But fortunately, at that time, maybe the experience of Nikolai Vavilov, who died during the war in 1942. So here is 1945. So maybe Stalin thought that perhaps it's important to save the scientists, perhaps for some use. So after spending some period, maybe a year or more, in a labor camp, and perhaps already on the verge of death, Nikolai Timofeev-Rissovsky was not released, but he was sent to a secret laboratory which worked on radiational genetics. Okay, and after Stalin died and Khrushchev declared, spoke about the crimes of Stalin, or the cult of personality in 1956, Timofeev-Rissovsky was released out of this secret laboratory and allowed to live not in Moscow, but in a city Obninsk. Well, obscure city perhaps for foreigners, not far from Kaluga, but very much known to Russians, I think, because it was the so-called scientific city, or Naukograd. Well, the city of scientists. Okay, there are some cities of scientists like Dubna, Pushchina, and Troitsk, and also Obninsk. So in Obninsk there was the first nuclear reactor which worked for peaceful purposes. Okay, well, so it was a town of physicists. So Nikolai Timofeev-Rissovsky was allowed to live in Obninsk, and he met, because he was very active personality, so he met with physicists, with biologists, and so he was quite prominent figure in Obninsk. Sometimes perhaps traveled to Moscow, or some people from Moscow traveled to Obninsk to meet Nikolai Timofeev-Rissovsky. So he was also like a remnant of this epoch. Now, perhaps you can ask, what was wrong with genetics? Why genetics was declared a pseudoscience in the Soviet period? So this was the continuation perhaps of the same idea of intervention of Marxist philosophers into science. It started with Lenin, his criticism of Mach, where Lenin formulated an interesting phrase that those professors, well, he just used this word derogatively. These professors are not to be sort of believed when they speak about philosophy, because they are all bourgeois. Their ideology is bourgeois. So if they do science, for example, physics or mathematics or biology, we can say, then we can believe them. They are like in their investigations. But when they start to philosophize on their on their discoveries, we shouldn't believe them. Okay. Well, this went sort of this was the opinion of Lenin. Now, what changed with Vavilov and genetics? Now it was not only the philosophical interpretation of genetics was called in question, but also the data themselves. So just genetics as a science was called pseudoscience. So not only the sort of philosophical implications or philosophical conclusions out of genetics were called in question, but genetics itself. So Mendel's law was declared pseudo law, and there was a so-called derogative term, Mendelism, Morganism. There was another important geneticist, Morgan, who just continued this work of Mendel. So, well, Bateson was not was maybe too small a figure to be included in this propaganda. So the targets were Mendel and Morgan, and all those who defended genetics were called just pseudoscientists. They were not allowed to continue to teach genetics. So Mendel's laws were prohibited, called erroneous. So it was like it was a terrible situation for scientists, because of course they could see multiple experimental confirmations of these laws. And now if we speak about genetic engineering, it seems childish. Yes, Lysenko, yes, of course. Well, I will speak about him. I just want to before we make a short break, just to finish with the overall situation, just because I think Lysenko, of course, he was like a pupil of Vavilov, and Vavilov helped him, and was like we can say that at the first stage, Lysenko was a protege of Vavilov, and Vavilov helped him even financially. Well, but then Lysenko understood that something is happening in Soviet ideology, and so Soviet ideologists need a new interpretation of biology. So he like unearthed outdated Lamarckism. You remember Lamarck and his philosophy of zoology. We spoke about that during our previous lecture. So he unearthed this Lamarck with his idea of inheriting acquired qualities. Okay, so it was, of course, well, perhaps in the beginning there were some scientists even abroad who played with these Lamarckian approaches, and even now they say about neo-Lamarckism, or the possibility, say, of bacteria to sort of acquire like resistance to antibiotics, and then to like to send this newly acquired quality to their its descendants. Well, I think biologists can speak more more qualified way about this problem. But here is like a appearing of something that can sort of remind us of Lamarckism, okay? But Lysenko went far. First of all, he was personally unscrupulous, and he sort of started to this campaign of discrediting Nikolai Vavilov, okay? And there were other people who helped Lysenko among the philosophers, so-called, because philosophers, of course, they didn't understand anything but they seized the opportunity to prove their usefulness to the state. So it was a great campaign. If we take periodicals of that time, like, for example, Under the Banner of Marxism or Questions of Philosophy, we'll see a lot of articles devoted to denunciation of genetics ideology from the Marxist point of view. It was taken as a banner, obscure article of Engels in his Dialectics of Nature, where he speaks about the evolution, how he understood it, Darwinian evolution, as the process of inheriting acquired qualities. So he said that labor made man out of ape, because while laboring, this primitive man developed, and his acquired habits were transmitted to the through inheritance to his descendants. Okay, so it was so Engels was interpreted in Lamarckist sense, and Engels was one of the pillars of Marxism. So Engels is much more valid than Nikolai Vavilov or Bateson or Mendel. You understand who is Mendel and who is Engels? Okay, so can you compare these figures? So I'm describing the general what happened in the Soviet. It cannot be understood, say, by even or by foreigners, of course, but even by modern young people of Russia. They cannot understand. Only such people as me, who lived through some period of Soviet Union, can understand the seriousness of all what happened. It was deadly serious. It was not just a play with words, okay? It was not a discussion like between, say, second positivists and Marxists before the revolution. So it was now the question of life and death for many, and for Vavilov himself. And happily, Nikolai Timofeev-Rysovsky managed to survive. But of course, he understood very well what happened during this time. Well, that's just a short survey, of course, of what happened in the 20th century, how this discovers or formation of genetics, which now change the face of the earth. If we take this genetic engineering, this subject was already touched by some of my students, even in connection with the medieval science. Well, of course, you can say that, say, this is a question of church intervention in scientific fields. So, for example, if the church will take a strong position against genetic engineering applied to humans, then we can speak of some connections with the Galileo cases like that. So of course we can speak about this problem now, and it was spoken. So, but we see that here we have quite so this like way from Mendel's experiments on peas to modern genetic engineering was sort of not so smooth in the Soviet Union. Okay, so maybe it led to certain like backwardness of Soviet biological science, which was felt even in the 60s of the previous century. Well, this is how it goes. So, now we'll make a break because we have to touch another very important subject, a revolution in physics, because there happened two major, I would say revolutions, the creation of special and general theory of relativity by Albert Einstein, and the creation of quantum mechanics by Heisenberg, Bohr, and Schrödinger. Oh, and Max Planck, of course. So after a short break, we'll speak about these subjects, okay? So now I just will ask you for a 5 minutes break, okay? Okay. Okay, sorry for a break which took more than 5 minutes. Now, please, Marina, if you are still here, show us the slide with Max Planck. Okay. Yes, here. Okay. Thank you very much. So you recognize perhaps Max Planck and his book, A Survey of Physical Theory. Well, it was just a lecture. The first, like the core of this book is formed by a lecture which Max Planck delivered in Berlin University in October 1913. So you know, also it was a fateful year. You remember Berlin, 1913. If you have a sense of history, you could understand that perhaps half of those who were present at this Max Planck's lecture were conscripted in the army, and perhaps many of them also died next year or maybe in the 4 years of the First World War. So at that time, it was all peace and nobody could just understand what is in store for Germany and for whole Europe. At that time in Germany, there was, of course, a kind of a nationalist spirit, but without any excesses, only that there was a celebration of the 100th university of the whole so-called Leipzig battle. Perhaps this battle is now not everyone can remember it. What was it, this battle? Maybe Vasily Vasilchenko has an idea what was this Leipzig battle of 1813, 100th anniversary of which mentioned Max Planck in his speech. Vasily, do you know, have you an idea about the Battle of Leipzig? It's called Battle of Peoples. Well, maybe Javier Ramirez knows something about Battle of Leipzig. Who is has information about the history of Europe of the 19th century?
About the Leipzig battle, it's the first time I heard about it.
Leipzig battle, between whom and whom was it fought? And who was victorious in this Leipzig battle of 1813?
Maybe it was a coalition of Alexander I and
yes,
against Napoleon.
Germans and Austrians. Yes. And who was the enemy of them, of this
Napoleon.
coalition? Napoleon, yes, exactly. Thank you very much. So now we have the idea. The Germans were victorious. So that's why this Battle of Leipzig, as in Russia, the Battle of Borodino, is regarded as a most important event, one of the most important events in German history. You know, this lecture of Max Planck coincided with the 100th anniversary of this battle. So Max Planck in the beginning spoke about this battle and the anniversary because he was at that time, I think, rector of Berlin University. Well, and then he started to speak about what concerns us, the revolution which happened in science. So it was a survey, and a survey made not by, say, like some amateur, but by one of the participants in this revolution, one of the revolutionaries, okay, we can say, because Planck's constant and Planck's formula was at the beginning of one of those revolutions. So Einstein and Planck can be regarded as main figures in this revolution. So so Max Planck underlined three important changes which happened in science, with truly revolutionary changes which happened in science at the at the end of the 19th and the beginning of the 20th century. The first, according to Max Planck, the first change was like falsification of the thesis of the indestructibility of atoms. So this leads us to the theme of our first lecture, atomism. So you remember how Democritus started this new, coined this new term and started this atomistic hypothesis or atomistic, we can say, research program. It was followed by say Boscovich and I think to a certain extent by Newton, and but at the 19th century it was already well established fact and considered one of the pillars of the classical science, that there are atoms out of which are formed molecules, and these atoms we have say about 80 or 90 exemplars of such atoms, and they were put into a certain order by Dmitry Mendeleev in his Mendeleev table. Okay, so this idea of Mendeleev appeared in 1869. Okay, there was a Mendeleev table was proposed for the first time. So so there was full consensus between chemists and physicists that these atoms are indestructible. So they are like units of nature, and so these atoms were regarded in this etymological sense, that undivided and cannot be cut in certain simpler parts. Okay, well, you remember, of course, Kant's antinomy, second antinomy, that Kant already doubted the validity, philosophical validity of this concept of indestructibility or indivisibility, and he already just showed some reservations whether it is so valid as it seemed to be. But Kant was forgotten. This was for philosophers. Scientists didn't care, and only one voice was sort of dissident voice was heard from Ernst Mach, whom we mentioned in the beginning of this lecture, who was a representative of the so-called positivism. Mach was a physicist, you know, this cone of Mach and the optics of the book written by Mach about optics and mechanics. So he was a very prominent physicist with his own discoveries. But he was skeptical about atomistic hypothesis produced by his compatriot Ludwig Boltzmann. So there was a great discussion between Boltzmann and Mach. Boltzmann was an adherent of atomic theory, you know, this kinetic theory, okay, with which he explained the pressure and temperature and other characteristics. Also, you know, of course, the Boltzmann's constant, K. Well, I think it's everywhere, K, okay? Boltzmann's constant is somehow connected with Planck's constant. Well, there was, of course, dissident voices, but the majority believed that, in fact, Boltzmann was right. But then what happened? Marie Curie started, and Becquerel first, and then Marie and Pierre Curie started experiments and with the salts of uranium, and they soon found that the so-called phenomenon of radioactivity. So atom, which was considered to be stable, indestructible, turned out to be unstable. This was the first sort of revolution which Planck mentioned in his lecture for students. Of course, it was a, you see, there are no formulas, there are only words, as with me. So it was a lecture for, I think, all students, not only physicists, because I think it was kind of a rector speech, okay? So he spoke in popular terms, and this is, I think, good for Skoltech, because I'm not speaking only to physicists, but also to petroleum engineers or computer scientists or biologists who, well, perhaps they studied quantum mechanics or general or special theory of relativity, but maybe have forgotten something or just don't. And I also studied it when while studying in physical department of Moscow University. But of course, something is forgotten and the details are somehow lost. But the general idea remains that the phenomenon of radioactivity just put an end to this idea of indestructibility of atom. So atom was now, it was understood that atom is a complex system. Then followed the so-called Rutherford experiment, which was conducted not by Rutherford himself, but by his pupils, Geiger and others. And the results were published in 1911. It was called the planetary model of atom. Well, so now atom is proved to be not indestructible, but a system, a complex system consisting of many elements, okay, like electrons and the core, nucleus. Well, then followed the discovery of protons and neutrons and so on. Well, so this was the, well, of course, Planck doesn't speak about protons and neutrons and even doesn't mention Rutherford in his lecture, but he speaks about Marie Curie and her discovery of radioactivity. He considers it to be the first breakthrough and the first revolutionary sort of event in the history of science at the threshold of the 19th and 20th century. Now the second, according to Planck, the second important event, revolutionary sort of breakthrough, was the Einstein's insistence on unchanged or constant, how to say, that the speed of light is unchangeable, that it is constant. It doesn't depend on the on the speed of the source of light? Well, according to Galileo, of course, the two velocities, the velocity of the source of light and the velocity of light itself, should be just added, and the result speed will be, say, c, the constant of light, the speed of light, plus v, the velocity of the source. Okay, so this was obvious because scientists in classical mechanics knew no other like transformations than the transformations of Galileo. Okay, they were called in such a way, transformations of Galileo. Now they had to give way to so-called Lorentz transformations, because otherwise this postulate of the constancy of the speed of light and its independence on the velocity of the source would not be saved. So this and also it was interesting that if we take these Lorentz transformations, they will then the so-called Maxwell's equations would be invariant towards this Lorentz transformation, not to the Galilean transformation. So we could have found them just solving a mathematical problem to find a set of transformations which which makes invariant the equations of Maxwell. So this is also a possibility. But Einstein went by other way, but he reached the same results. Well, of course, if we continue this so-called the description of this revolution in brief, we can say that it ended the so-called, well, it sort of put into doubt the very important postulate of Newton, the unchanged nature of mass. You remember the second law of Newton is, we can even speak about it with children. F, or force, is equal to m, or mass, multiplied by a, which is acceleration. Okay, so now if we just blindly follow the second law of Newton, and if we say that mass is constant and doesn't depend on speed, then we can say accelerate a small particle, for example electron, in a very, say, force in a very high magnetic field, or in the accelerator, say in Dubna, to any speed, because we can apply force, and with time the acceleration will change his velocity to any value we want, even higher than the velocity of velocity of light. But according to Einstein, his postulate, velocity of light is not only independent on the velocity of the source of light, but it also cannot be sort of overcome, or there is no velocity that can be higher than the velocity of speed. This is a postulate of Einstein. So something should be changed with this Newton's equations, with the second law of Newton. And the change concerns mass itself. So mass is now dependent on the speed of the object. So when the object starts accelerating and reaches the speed which is compared somehow with the speed of light by magnitude, then its mass starts to grow. Well, this was quite new. Well, Max Planck didn't mention that because he didn't want to go into details, but this is one of the conclusions of this Einstein's postulate on the constant velocity of light, and the velocity of light being the greatest velocity possible in the world. Okay, so now we have another formula energy is equal to m multiplied by the square of c, velocity of light. Okay, this is one of the most important breakthroughs in the physics of the 20th century. So mass now depends on energy. So there's connection between mass and energy, which was unthought of in classical mechanics, where energy is one thing, we say kinetic energy, so m was regarded as and there was also some interesting well, I would compare it with the Platon's allegory of the cave. You remember that when we were taught kinematics or cinematics at school, we were told just to write down the formula for kinetic energy. And they say, well, remember, please, children, how to find kinetic energy. You should take mass, multiply it by square of speed, and divide it by 2. Okay? So, and we took it just as the prisoners of the cave took these shadows on the wall without any argument. So the teacher showed us this formula. So what we have to do is just to solve the problems in our textbooks, you see, and receive a good mark. Okay, so the most simple task was that the mass is equal to 60 kilograms, the velocity is 10 meters by second, and just count the kinetic energy. So the most able students just put this, those who understood, who followed the teacher, they just put these values into the formula and received more or less a good answer, okay? Depending on their abilities to multiply or divide. Well, nobody asked a question why it is mv square of speed divided by 2 and not by 3 and not by 4. Okay, so we took it like children take the catechism, that there are 3 persons in the Trinity and not 10. Okay, so nobody questions the priest, they just learn it by heart. And so the same was our attitude towards this called cinematics or kinematics. Okay, now Einstein shows us why this 2 appears. So it's a second term in Taylor Rye or Taylor sequence. If we well, I will not go into details, but if we take the formula for m is m0 divided by the square root of 1 minus v square of velocity divided by square of light of speed. So then if we then just take that, just this function can be sort of resolved into this Taylor sequence. Okay, so the second like member will be exactly m v. For low speeds it will be just m. The first will be m0 multiplied by c in square of c of velocity of light, and the second will be exactly m multiplied by the v in the square of v divided by 2. So this 2 appears as a result of a more broad or more general approach. Okay, so it's not just be taken just without any explanation, like the prisoners of the cave just took these shadows sort of without questioning why these shadows and what is the sequence of these shadows. So now we have seen the light. Okay, with Einstein sort of delivered us from the cave and showed us the light. Okay, so we now see the reasons of what we just blindly believed when we were school children, okay? Or when all people believed when, since Leibniz introduced this, say, formula for kinetic energy in the beginning of the second, so say, revolution, the revolution conducted by special theory of relativity of Albert Einstein. Then the third mentioned by Planck was the revolution in which Planck himself took an active role. This is a break with a continuous theory of matter and introducing of quanta, or of, say, jumps, quantum jumps, okay? So here you see underlined is this Latin sentence which was used by Planck, natura non facit saltus. Well, this Latin expression, which is in original of Planck's lecture, delivered of course in German, and here it's also concerned here in this English translation, this can be rendered in this way: nature doesn't make jumps. So there's a principle of continuity, established by Galileo and then confirmed by Leibniz. So in nature, everything happens continuously. Well, if we take, for example, acceleration will also is a continuous process. So we can find the so-called momentary speed in every point of the time axis, okay? So if we take this axis v on the y-axis and the t, or time, on the x-axis, then we'll have a continuous function, v dependent on t. So when some object starts to accelerate, it's, according to Galileo, it starts from the minimum of slowness. So according to Galileo, in order to reach, I'm just citing more or less verbally Galileo. So in order to reach some speed, the object must pass through every stage of slowness, tardità in Italian, or tarditas in Latin, so slowness. Okay, now of course you don't use this word slowness. It's Aristotelian, you see, because Aristotle always divided between dry and wet, hot and cold, so slowness and fastness. Okay, now we use just velocity, temperature, and humidity, and you understand. So now things have changed, but Aristotle, in order to, Galileo, in order to be understood, used this obsolete word of Aristotle, tardità, or slowness. But the meaning is quite clear, I think, that in order to reach some velocity, the object should undergo pass through every stage of slowness. This is the continuity of motion. Now this continuity ended. So, unfortunately, Max Planck didn't cite this example because it was not yet formulated. You remember this 1913, and in the same year appeared so-called Bohr's postulates. So Niels Bohr, like Einstein, also produced postulates. According to this postulate, for example, angular momentum of electron in atom should change not continuously, but by jumps from it dependent, it should be like certain, how to say, this Planck's constant, because it has the dimension of angular momentum, was regarded as a so-called quanta of angular momentum by Niels Bohr. So according to postulate of Niels Bohr, electron in the atom, say hydrogen atom, had only well, should just jump from one angular momentum to another. Well, this, how to say, the width of this jump is Planck's constant, okay? So this was quite new, because according to classical mechanics, angular momentum should also be continuous. For example, if the speed, well, angular momentum is a value sort of, it's m, or mass, multiplied by interval of space c, s, and multiplied by v, the velocity. Okay, so these three values are multiplied and we have angular momentum. Or if you don't take c but you take radius r, okay, because radius of the orbit. Okay, so of course, radius of the orbit, say, is constant. We don't take it, but mass is also constant, but v can change. So velocity can change because velocity is continuous. So why should we speak about these jumps of angular momentum? Because, well, it seems that you can get any value for angular momentum as we want. But Bohr said no. There's a quantization of angular momentum, like quantization of charge. At that time, there was already known that electric charge is also quantized. You know, that's the quanta of charge. So at first, this quantum appeared with quantum of charge. Then it appeared with Max Planck's theory, quanta of light, that light is also somehow not wave, but also a corpuscle. There's a light quanta sort of introduced by Max Planck himself. Okay, so energy of these quanta are dependent only on the frequency of light and not on nothing else. Okay, so the related formula is E is equal to h multiplied by nu, where nu is frequency and h is the Planck's constant. Okay, so now we have three breakthroughs in science. Okay, well, maybe excuse me for being too unprofessional in knowing the details and forgetting perhaps some exact terms here, because I didn't study English in physical. While studying in physical department, I was given another language, German language. So that made me quite bad expert in technical English, technical translation. So I'm good when it comes to, say, philosophy and religion, and my English becomes less and less precise when I speak about physics. It's just irony, but or mathematics, but that's you should somehow take it into consideration. Well, maybe you will find a better lecturer next time and he will explain it to you in better way. But here we are now. So I hope that the gist of these problems are understood by you. Now, what remains before we make a break, we're a little bit sort of, well, but I will make a break just in 5 minutes. Before I finish, I want to speak about a great controversy which happened among these two authors of postulates. You remember, the first postulate was made by Einstein. This postulate, there are two postulates. There's equality of all systems of reference and the constancy and unsurpassable character of the speed of light. And Bohr also made postulates and one of the postulates was the quantization of angular momentum of electron in nucleus. So these two great physicists and two revolutionaries couldn't sort of live with each other peacefully. They started to argue. And the point of the argument was the determinism in nature. Because according to Einstein's special theory of relativity, we can speak validly speak about causation, that that the events that happened in the past, if they can if the information can pass from them by the speed lesser than the speed of light, they can influence the present. Okay, so but there are also other ways when events cannot influence the events of the present. For example, the future events, according to Einstein, cannot influence present because they belong to another type of interval. If we take the interval between events, it can be either space-like or time-like. And if it's time-like, well, excuse me if I'm wrong, then there can be no causation. And if it's space-like, then there can be causation. So, but causation is there. So Einstein was a firm adherent of causation in nature, that everything is determined by cause. And if we don't know this cause, we should seek for it and not stop our attempts to find the cause of all the events that are around us. With Niels Bohr, there was these jumps had no causation. We couldn't explain why these quantum events happen and when will they happen. Also, radioactivity was founded by Marie Curie, was rethought as a quantum process, especially by Gamow in his idea of quantum tunneling and others, well, by Schrödinger equation, of course. And so the radioactivity could be described as a chance process of which we know only the probability that it will happen, but we don't know the exact time when, say, a radioactive atom will decay. Okay, so this was unacceptable for Einstein because he said, no, there should be some cause for radioactive atom to decay at this precise moment. So we don't know. There are some hidden parameters that govern this process of radioactive decay, which we are ignorant of. So we should find it. And Bohr said, no, this is my postulate, that this is a really chance event, that we cannot speak about these hidden parameters. And here Niels Bohr was also on the side of Ernst Mach and second positivists, who said that we shouldn't speak about unobservable qualities or so-called hidden qualities. Like Einstein himself, when he sort of said goodbye to the concept of world ether, he also was following Ernst Mach in a certain sense, that this world ether is unobservable. The results of Michelson experiments are negative. So what's used to speak about unobservable entities? Well, here the Niels Bohr followed Mach principle, and Einstein curiously shared the position of objective realism close to Lenin, but he, of course, didn't speak about Lenin. He preferred to speak about Benedict Spinoza and his objectivity and his determinism. So, well, Niels Bohr also had to find some philosophical figure which was like a precursor of his approach. Well, he could have applied to Kant and his principle of things in themselves, which cannot be known by us. So radioactive atom is an example of such thing in itself, okay? So we cannot know when he will decay. It will decay. But there also is an interesting example of a philosopher, also Danish, like Niels Bohr, Søren Kierkegaard, who also spoke about jumps, but only in the domain of religion and ethics and philosophy, but not in the domain of physics, of which Kierkegaard was quite ignorant. But the idea of a jump was already present in Kierkegaard's philosophy, and it was associated with human freedom. So we can just use this formalism to illustrate Bohr's approach or Bohr's position. Well, now much literature is written about Bohr and Kierkegaard because it's interesting to compare two Danish, one physicist and one philosopher. And also it's interesting to compare two Jews, Einstein and Spinoza, okay? So it's just very illustrative, okay? But maybe, well, you can find other examples, just nationality, or it's not so much important, especially if we take into consideration that Niels Bohr was half Jewish, I think, by his mother. So, well, this is, of course, this is not a question of national conflicts between Danish and Jews, but it's a conflict of worldviews. And here Bohr and Einstein represent the so-called determinism and indeterminism. Well, with that just observation, I want to finish this part, and then we'll speak about universe after a break, okay? And well, I hope we'll somehow manage this topic also. Thank you. So let's have a break. Marina, please. I can here also do it. Okay, let's continue because we have a long way to still to pass. We'll speak about now the expanding universe, or how it all started. First of all, we should start with the so-called Uneuclidean geometry proposed by Lobachevsky. So it was just at first it seemed just like a mathematical trick kind of, and not related closely to physics. But if we remember this Pythagorean approach that numbers rule the world, or we can say geometry also rules the world. So perhaps this event in mathematics can be some later could find some illustration in physics. Well, unfortunately, I'm not competent, Alina, to speak about Dirac-C. Maybe I will write to you privately when you will cover this topic in one of your essays. So now I'm afraid I'm just you test me beyond my possibilities. Okay, so I will just like to speak about this how I plan to speak about expanding universe. So I start from Lobachevsky. Then there was a maybe not so important astronomer, German astronomer, Zollner. Well, but you can find information about him. He published his book, well, about the comets, I think, in 1872, where he proposed the this solution of, say, Olbers paradox or photometric paradox, or we can say also gravitational paradox, that infinite universes contains paradoxes. It was observed not only by Kant, because Kant paid attention only to philosophical paradoxes of infinite universe, but it also there could be physical paradoxes. For example, photometric paradox, that like brightness of the sky would be infinite if there will be infinite number of stars in the infinite universe. If there's finite number of stars, then it always is a question why they are concentrated in a certain limited volume of the infinite vacuum. So this was all very improbable, and there was a kind of a discontent among physicists about that obstacle, or about this sort of thing, like difficulty. And Zollner proposed interesting solution. So, for example, if we take dimensional sphere, then its surface will be three-dimensional. So we can just abstractly regarding it like Boscovich, you know, without any confirmation from the experiment, just an abstract idea that suppose we live on the surface of a four-dimensional sphere. Then, of course, because this surface is, its dimensions will be -1, so it will be, the surface itself will be three-dimensional. But we are living in three-dimensional world. So now, at first, Kant regarded this world as a unique possible, because according to Kant, we can't imagine the world either than three-dimensional and Euclidean. But now, from the mathematical point of view, we can, taking in view Lobachevsky's un-Euclidean geometry, so we can take this concrete example of un-Euclidean geometry. It's, say, the surface of the four-dimensional square, and then all the paradoxes would be solved, because as we can say, calculate the surface of this, of say, three-dimensional square. We can calculate this, the surface of it, the square of this surface. So the same procedure we can make with the surface of four-dimensional square. So it will be finite, of course. So this, but it will look as if not infinite, but endless, because we can travel like we travel, say, around our Earth. We can travel and travel and never find the end of our Earth. Suppose our Earth were flat, then we could find the end, okay? But because it is round, because it is spherical, we cannot find the end. So in the same way, if we travel by the surface of the four-dimensional sphere, we will travel in 3 dimensions, but we will never find the end, okay? So all the paradoxes are solved, and also is somehow solved the first antinomy of Immanuel Kant. So the world can be endless and at the same time finite, okay? But these were all speculations, just without any experimental confirmation, or without any set of equations. What did Einstein in his general theory of relativity is to give to this just mere imaginations a concrete example. So now it was sort of from the set of equations which started from a postulate of the equivalence of the inertial and gravitational mass, and Einstein came to this solution which was proposed by Zöllner just abstractly, that we live on a certain kind of a surface of a four-dimensional ellipsoid, okay? Now, this ellipsoid was thought of Einstein as stable, and he introduced even a certain member in his equation to provide the stable character of our universe. You remember, with Spinoza, we also have this stationary, stable universe. We discussed this question of Spinoza's philosophy being sort of not evolving, okay? So Einstein liked Spinoza and wanted his universe to imitate the universe of Spinoza. So it should be stable, it should be, and it should be finite in order to explain all the paradoxes. And Einstein himself, in his 5th memoir on general relativity, written in 1917, he expressly says that my theory, general theory of relativity, solves the gravitational paradox, which remained as an unwanted legacy from Newton, okay? from Newton's infinite universe. So this finiteness it's okay with that. But now, what did Alexander Friedman do? Alexander, we mentioned him when we spoke about Soviet science. Alexander Friedman. Sorry, Friedman. Well, he in 1922, he proposed the solution of Einstein's equation, which would sort of give us expanding universe, unstable expanding universe. So it is also non-Euclidean. It's also perhaps can be regarded as a three-dimensional surface of four-dimensional ellipsoid, but it is also expanding. So the radius of this universe, or the radius of this imaginary ellipsoid or sphere is changing with time, is growing with time. Well, as I told you, Einstein was not happy with that solution at first, and said that perhaps there are some mistake in Friedman's calculations. But then other people who regarded it independently, they saw that Friedman was absolutely right, and later Einstein had to sort of recognize his mistake and said that it was the biggest blunder of my life. Okay, the biggest. You can just sort of Google this word, the biggest blunder of my life. I don't know whether they were said in German or in English, because Einstein was bilingual of my life. Well, of course, his native language was German, but he also, and perhaps he was thinking in German, but he was also writing in English also. The biggest blunder of my life. Okay, and then we have already spoken about controversy between Bohr and Einstein, but here is another controversy with Alexander Friedman. Unfortunately, Alexander Friedman could not continue this discussion because he died in 1925. But in the same year, I think 1925 or 1927, there appeared the discoveries made by astronomer Hubble, Edward Hubble, I think, who was not an expert in general theory of relativity or theoretical physics. He was just a practical astronomer who just tried to find the distances from two distant galaxies. Well, he used the so-called Cepheids, the stars which have periodically, that's how to say, their luminosity is periodically dependent on time. It's decreasing and increasing just with certain period, okay? Of variable luminosity, we can say, the stars with variable luminosity. They're called Cepheids. Well, why they're important for sort of calculating the distances to galaxies? Because we can compare their visible luminosity with their real luminosity, which depends on the period. So the period doesn't change, but the luminosity decreases with distance. So by regarding the period and understanding their real luminosity and comparing it with the observed luminosity, we can make some estimations of how distant those Cepheids are. And so he was able to find more or less the distance to the Andromeda Nebula and other nebulas. And then, well, it was a very good piece of astronomical work. But then Hubble, just regarding the spectra of these galaxies, he saw that like the lines of the spectra are sort of, in most cases, not in the case of Andromeda, but in other cases, in most cases, they are shifted to the red. So this called so-called redshift. Redshift. Well, redshift. So how could it be explained? And then if we compare this experimentally found by Hubble redshift with Alexander Friedman's idea of expanding universe, then we can come to the solution that perhaps the universe is expanding, and this redshift is nothing other than Doppler effect. Okay, so these galaxies are sort of moving away from us with a great speed. Well, this solution prompted another scientist, Belgian scientist, Georges Lemaitre. Maybe we have a photo of him, Marina. If she left, then she will show us when she returns. Marina, here it is. Okay, so here's Lemaitre solving, I think, Einstein's equation or something like that. Just displaying how the distances to galaxies grow while the universe is expanding. Okay, so he just give us the how the Hubble law is explained in frames of expanding universe. And here's just his portrait. You see the color, the white color, white collar. I'm sorry, white collar. This is typical for Catholic priests. So we have by chance today another Catholic priest. Not that I just invent them just for the sake of propaganda of Catholicism. No, you understand, it's far from my intentions. But somehow they come into the history of science. First it was Boscovich, then it was Mendel, and now we have Lemaitre. Well, women also appear like Marie Curie, so many people appear. Indians perhaps also in explaining the supernova explosions. So, well, unfortunately, I can't speak a lot about contributions of every civilization, of every race, of every nationality to science, but and also occupations, so priests or laymen or believers or unbelievers, all of them of course are taking part in this process, but it would be not wise to discriminate any participant because of his religious religious convictions, or because of his just the color of his skin or his nationality or any other, or his gender. So if a person does something really important, then we should include him in our sort of survey. So that's why I included Georges Lemaitre. Now, well, with Lemaitre, we have this the so-called primeval atom and its explosion. Later, there was coined the term Big Bang. And we have the book of Steven Weinberg, first 3 minutes, I think, yes? Marina, do we have this slide with Steven Weinberg book, first 3 minutes? No, don't have it. Okay, then we can find it just, here, yes, Steven Weinberg and the first 3 minutes, the modern view of the universe. Now we have, all the, Steven Weinberg is also a prominent physicist and also a revolutionary kind, and his contribution to particle physics is very important. But now we can have the whole picture here if we read this book. But Steven Weinberg is not a historian, so he will not speak about Zollner, Einstein, Lobachevsky, Friedman, Lemaitre in great details. We can also mention Gamov. We already mentioned him with tunneling, and now he proposed in the 40s already this idea of hot universe, which is sort of becoming colder. And now, how can we measure the temperature of the universe? But we can measure it not directly by just a thermometer, but by measuring the energy of the of light, which was sometimes which was in thermodynamical equilibrium with the universe, and now this light has the frequency which sort of corresponds to 3 kelvins. So now we can say that the temperature of the universe is 3 kelvins. So the universe is cooling down. But in the beginning and the initial stages of this Big Bang, our universe was hot. Okay, so this was the idea, Gamov's idea of hot universe. Okay, well, now we how we get to know that our universe is now cold and has a temperature of 3 kelvins. That's because of the discovery of the so-called background radiation, which was done in 1960s by Penzias and Wilson, two prominent also physicists and astronomers. Okay, they received the Nobel Prize for this discovery. So now we have all this put in a certain package, and I can sort of refer you to the book of Steven Weinberg, but maybe there are other books by Stephen Hawking also about the expansion of the universe and Big Bang cosmology. This is called the Standard Model. Now, what is interesting is that when how it was received by general community or by philosophers or by just literary men, by general public. Well, first such, how to say, indications that it produced some important impression on people, on, say, belletrists, is the Anti-Utopia by Zamyatin, Evgeny Zamyatin, a Russian author. Marina, can you please just stop the presentation so that I could write Evgeny Zamyatin in chat, okay? So, Zamyatin. Well, for Russians, it is more or less known figure, Zamyatin. Well, for English or well for others, well, I can say that he is a prominent Russian belletrist and the author of Anti-Utopia We, which is called just We, which influenced two great anti-utopias, the anti-utopia of Aldous Huxley, Brave New World, which is of course much more known, and Anti-Utopia of George Orwell, 1984. So they were influenced by Zamyatin, and there's a lot of literature about that, articles written about Zamyatin and Orwell, Zamyatin and Huxley. Well, and so 1984. Okay, so now returning to We of Zamyatin. There's an episode in this Anti-Utopia when a certain physicist, well, just in a public toilet, this is interesting detail, they are hiding from some police operation, and they're hiding in some toilet, underground toilet, and there they meet these two people, the main hero and a certain physicist. And the physicist says, well, I have recently found a solution that our universe is finite but endless at the same time. Okay. And I want you to, and you are the first man with whom I share this new solution, this new vision of the universe. And at that time, when they were talking in this toilet, the police entered and took them for operation on their brain. After that, they started to think in line with the party line, okay? So, because in this anti-utopia, everybody should think as is asked of them, not just no dissident thinking is allowed. So and those dissidents who don't want to align their thoughts with the party line are to underwent compulsory operation on their brain. After that, they would only just give the ideas that are in line with a certain ideology of the party which is ruling in this imaginary state. Well, of course, Zamyatin just hinted at communist dictatorship, but this novel was written already in 1921. So we can see that it was written even before Friedman's equations. Well, but perhaps Zamyatin, being an engineer and an educated man, he got acquainted already with some information about Einstein's theory of general relativity. Okay, so there's the first example how physics enters big literature. The second example is, of course, the novel of Thomas Mann, German writer Thomas Mann, which is called Dr. Faustus. Well, it's a novel. And here we have just a brief description. The people are talking, composers are literary men, they are in the novel, and they also discuss expanding universe. So Dr. Faustus. Dr. Faustus. Faustus. Well, you can read it, maybe you've read it. It's a very celebrated novel of Thomas Mann. So now we see how these abstract physical theories enter into people's consciousness. Okay, and but in Russia, of course, the Soviet Union was not very close society. We had some rumors from abroad, but they were censored sort of by Soviet ideologies. So these three theories didn't fit, three physical theories didn't fit into communist outlook. First was a special theory of relativity by Albert Einstein. Already in the beginning of the 1920s, in the so-called in the periodical called Under the Ban of Marxism, there appeared articles denouncing Einstein's theory of relativity for its un-Hegelian, undialectic character, because speed of light does not change, remains constant. So it's like an invariant, this speed of light. And according to Hegel, as it was written, everything in this world is subject to changes. So there could be no invariance in the world, because it's contrary to Hegelian dialectics, on which stands the whole edifice of Marxism. Okay, so this was the first reproach to physics. Well, so physics, of course, physicists, of course, continued to use special theory of relativity, and it was also very important when they started the nuclear project to develop atomic bomb. Of course, the atomic bomb couldn't be developed without special theory of relativity, because it's sort of the concept of this bomb stands on this equation energy is equal to m multiplied square of c, the speed of light. Well, how this is under all these all these calculations. Okay, I will not enter now into details. So of course, for practical reasons, physicists were allowed to continue their investigations, but they were prohibited to speak about philosophical implications of their discoveries. Okay, that was a ban. So officially, if we read say articles in Вопросы философии or questions of philosophy, say of 1940s, there are still articles denouncing Einstein, his special theory of relativity, and others. Well, sometimes some just voices of dissent begin to appear after the death of Stalin, but not earlier. Okay, now quantum mechanics. Here the target of criticism of Marxists was the so-called Copenhagen interpretation of quantum mechanics, and namely this indeterminism. So here it is curious, the Marxist ideologies took the position of Einstein, the position of full determinism and criticism of indeterminacy of, or say, you understand that uncertainty relations of Heisenberg, they all were criticized by Marxist ideologists for idealism. But this idealism was just in this idea that we don't know the cause of quantum effects, okay? So it was also declared incompatible with dialectical materialism. So again, the same situation. They even tried to start a new ideological campaign, but it is a rumor that Kurchatov, together with Sergei Vavilov, just personally addressed Stalin and said that this campaign will sort of hamper the important investigations which lead to the creation of nuclear weapons. And because the nuclear weapons were the first priority for Stalin, so Stalin reluctantly just ordered his philosophers not to sort of start the campaign of the same scale as the campaign against genetics, okay? So this campaign never materialized. But if you read the articles in the same questions of philosophy or under the ban of Marxism, so you will find reproaches to idealistic Copenhagen interpretation. And even when I was a student, it was still regarded erroneous, and we were taught on the lessons of dialectical materialism that Copenhagen interpretation is false from the Marxist point of view. And the strict determinism reigns in the universe. Well, so, and Einstein was right in his discussion with Niels Bohr. And the same, of course, attitude was displayed towards expanding universe. It was called the invention of reactionary philosophers, which sort of backs the idea of creation of the world out of nothing by God. Okay, so it has also religious implications, that this expanding universe, because it somehow sort of confirms the idea that our universe is not eternal, that it has some age and also temperature. So this was considered to be idealistic and supporting the religion, okay? So religious outlook. So of course it was also not allowed to astronomers to defend this concept. And even my scientific supervisor, Nikolai Ovchinnikov, who was a physicist by his first diploma and then a philosopher, he said that Big Bang is a great fake of the 20th century. Okay, well, he now died. Perhaps he changed his mind, but I heard it from him that Big Bang is a great fake. So there was academician Logunov who proposed a new variant of solving the equations of Einstein, somehow defending the infinite concept of infinite and stationary universe. But of course, these were marginal, of course, opinions, and now we have the standard model, and only it is just added this idea of inflation, of which I will be silent because I'm not an expert here. It was born after I finished already the university, so well, I can have no good idea of how to explain it popularly. So you can, if you are expert there, you can write it privately in your essays, and I will try to find a sort of head or tail of it. Okay, so now we have more or less covered this topic of expanding universe. What is left? Well, of course we can speak about quark model, which is also resembles us a little bit of Aristotle, because when we introduce such qualities as strangeness of quarks, it can remind us of Aristotelian wet and dry, or say hot and cold. Okay, so the initial elements are also built out of qualities, sort of, you see, up and down quarks, strange quarks, and so on. So of course here we can find, if we want, also some reminiscences of Aristotelian approach. But I want just to finish my lecture with quite a new theme. I want to speak about psychoanalysis, because and about Freud, because this will be important for our last lecture, when we'll discuss, for example, Karl Popper and his falsification principle. There will be a thesis that Freudian psychoanalysis is unfalsified in principle. So it is, according to Popper, not a science, but pseudoscience, okay? So, but in order to understand what Popper means, and also Freud claims that he is a scientist, that he introduces a new like turn in psychology. So I think it is important just to say a few words about Freud and his, well, we can also say revolution in understanding of human consciousness, of human behavior. And I think it is an important theme also. Well, I ask you for 5 minutes just to collect my thoughts, and then we'll, what is left of this lecture will devote to psychoanalysis and Freud, okay? This is now just 5 minutes just for me to concentrate. Well, let's one last battle and we'll finish it all. Okay, so well, of course you can say why I'm speaking about Sigmund Freud, what uses of this dabbling into, or just digging into this pseudoscience, and perhaps negative, some of you are negatively disposed towards Freud and psychoanalysis. But still it's a part of culture and a part of philosophy, and because it was criticized by, say, Karl Popper, so we should know just what was it that Karl Popper sort of criticized. And so this will be like an introduction in what happened in the 20th century. Well, of course, we can say that if we take general philosophy, not philosophy of science, but general philosophy, of course, this like trinity, kind of a trinity, Marx, Nietzsche, and Freud are all sort of discussed as a makers or teachers of thought, or makers of our contemporary outlook. Okay, so perhaps there was also synthesis made by Herbert Marcuse. I'm sorry, I was just with a capital letter. Herbert Marcuse. He made in his book Eros and Civilization, he made like a synthesis of Marxism and Freudism. Well, also there are made some ways of synthesize Schopenhauer, Nietzsche, and Freud together, because of course there is some influence that can be proved between Freud and Schopenhauer, or influence of Schopenhauer on Freud, and also of Nietzsche on Freud. Well, let's start from the beginning. We have not much time, so again, we are in Austrian Empire, as with Mendel, so we start from the date of birth of Sigmund Freud. He was born in 1856, and he studied on the medical faculty of Vienna University. Well, Freud was a Jew, but according to, well, I think from the end of the 18th century, during the so-called liberal politics of Emperor of the Holy Roman Empire, Joseph II, it was the contemporary of Mozart, you understand, end of the 18th century. It was allowed for Jews to enter Austrian universities. Also, Jews were allowed to enter University of Prague and also University of Vienna. So this was nothing extraordinary that Sigmund Freud could receive higher education being a Jew and not a Christian in, say, well, also, one of the best European universities, Vienna University. Okay, he studied at the medical department. Now, here is some connection between also Freud and Spinoza. In what sense? Both were Jewish also, of course, but also Spinoza influenced Freud. In what respect? Not in determinism. Well, of course, determinism also is very important for Freud, because he wanted to find the cause of all psychic events, okay, of all our, so somehow he thought that in our subconsciousness there hides, like the hidden parameters of Einstein, the source of all our so-called free actions. So our so-called free actions are produced by way of causation by our subconsciousness. So here Freud was also on the side of Spinoza. But also what is important for Freud is not only this causal explanation of our psychological, so psychical, I would say, events, but also that this understanding of the causes of our emotions lead of our passions, speaking with the words of Spinoza, leads to our sort of to joy. So when we understand the passion, its causes, then this passion doesn't injure us anymore. We sort of, how to say, tame it, you understand, tame as an animal. So these passions are animals. Well, we can compare them with horses of Plato, but these horses can be tamed, okay, by our understanding of the causes of our passions. For example, anger or lust or any other, which you remember the 7 deadly sins of Bosc, So they all can be explained. And when we explain them, we sort of are liberated from their grip, okay? So this is this idea of Spinoza is very important for psychoanalysis. So the idea of understanding not only of passions, but also our neurosis, for example, or say insomnia or impotence or any others, hysteria, all these narcissism, all these sort of our sort of diseases, mental like disorders, if they are understood with the help of the psychoanalyst, they can be tamed and sort of cured. So cure by understanding, you see? So this also very Spinozist thought that that the receipt or way to cure our diseases, mental and neurotical disorders, are in their understanding of them. So when we understand the cause, then we can master them or cure them. Also, this is, of course, Spinoza speaks about this like aim of philosophy in his political treatise when he says that our motto should be not laugh, not shed tears, but understand. So we shouldn't be laughing, we shouldn't be shedding tears, but we should understand. This like stress on understanding, okay? So this is the core also of psychoanalysis. Well, it all started with, after Freud finished Vienna University, he went to France, where he just staged or worked in the laboratory of Charcot. Charcot. I think I've written him correctly. Charcot. This is a famous French psychiatrist. I mentioned you already Louis-François Lelout, who gave a diagnosis to Blaise Pascal, but now we have another psychiatrist, Charcot, who produced experiments on hypnosis on hysterical women. And during these seances of hypnosis, he sort of, how to say, gave orders to these hysterical women who were in trance to make some action after they come out of this hypnotic trance. And it is interesting that they have completely forgotten what these orders that were given to them by a hypnotizer, by Charcot himself. But they somehow tried to implement these orders, to obey these orders after they returned to normal situation. For example, if the order was to open an umbrella, so they blindly obeyed this order, notwithstanding that there was no rain. So when the hypnotizers, Charcot, asked them why do they open the umbrella, they say, well, that it can be rain. I will just prepare myself for starting for imminent rain. So they, of course, they couldn't understand that their sort of unusual behavior is caused by this directive which they received during the hypnotic seance or hypnotic trance. So for Freud, it was a kind of elimination. Now he says, well, when we sort of explain our actions to ourselves, we sort of rationalize them. So try to explain them rationally. But this real source lies perhaps in subconsciousness. So we are sort of in the position of hypnotized patients. So our subconsciousness contains the real reasons of our behavior. And when we try to explain our behavior by rational arguments, we are sort of ignoring substituting the illusionary causes for real causes, and the real causes of our sort of behavior, of our actions, lie in the subconsciousness. Now, how can we enter this subconscious realm? Through so-called through the interpretation of dreams and through our involuntary mistakes. Well, I produce during these 9 lectures, I've produced a lot of such mistakes, okay? For example, this lecture started with my mistake. I remember it very well, and I studied it, almost learned it by heart, this materialism and empiricism. Why did I make this mistake and try to write it Marxism and empiricism? So according to Freud, this my mistake sort of shows, or it highlights something within my subconsciousness, okay? So this is not just chance. This is association which exists in my subconsciousness between Marxism and materialism, okay? Of course, not all materialists are Marxists. I think the majority of my students are materialists, which I can just gather from your essays, but you are not Marxists, or maybe not most of you. So materialism is like a greater multitude than Marxism. Marxists among materialists are a small minority, we can say, or a multitude within a multitude, okay? So why do I associate them, put equal them, or you understand? It's just a mystery, but it can be somehow explained if I underwent psychoanalysis with an experienced, again a mistake, experienced, because I mix Russian's word opыт and the English word experience. So this is also something within my brain. So with an experienced psychoanalyst can explain me why do I make these mistakes. And of course, he will venture in the explanation of my dreams. So he will ask me to remember the dreams, and then we'll start interpreting dreams. But here, I think the science ends with the interpretation of dreams, because the interpretation of dreams cannot be subjected to any test, whether this interpretation is true or false. So it all depends on the intuition or on the conception of the psychoanalyst himself. He wants to interpret my actions in this way. So he has a theory of my mental constitution, of my ideology, of my motives, and he seeks in my dreams the confirmation of his already preconceived theory of who am I. And how he can understand me? Only by a certain kind of an intuition. Here we have a special system of reference connected with the psychoanalyst himself. Privileged system of reference, and I cannot do anything because he regards me in his frames, in his system of coordinates, okay, Cartesian coordinates. So he puts me in a certain place. He gives me a certain point where I belong to, okay, and regards me in frames of a certain concept, okay. This is perhaps I would say the weak point of psychoanalysis. That's why I'm just not eager to undergo psychoanalysis myself. I mean, to apply to an experienced psychoanalyst and to discuss with him my problems. Why do I make mistakes in presenting my lectures? Why it is not easy for me to remember certain words or expressions in English? Why do I just repeatedly forget or certain expressions or facts? So maybe it can be explained, but regarding that, psychoanalyst himself has his own worldview, and I don't fit perhaps in his worldview. So this will be a conflict of like ideologies, and this conflict will, I think, hamper good process of psychoanalysis. That's why I'm generally on the side of Karl Popper. So because of this lack of crucial experiment and this freedom in interpretation of dreams, we can say that this is not strictly scientific. But there are other philosophers of science like Paul Feyerabend and Imre Lakatos, and they just take another stand on Sigmund Freud and his theory. They say, well, if it sheds some light on your behavior, then it is already good, because explanatory function of a theory is also important. So if, say, when you see a certain, well, you remember we discussed Zarathustra, Nietzsche, this comparison with a cup which is overflown. Well, of course, Freud will substitute this idea of sexual energy, which is sublimated somehow in this like loner or hermit staying for say 10 years without sexual intercourse, for example, or sexual relations with anybody. So in this situation, it seems that a person accumulates sexual energy, libido, as Freud will call it. And so his creative potentials can be explained as a kind of a sublimation of this libido, of this psychic energy, sexual in its core, in, say, creativity. That's how Freud explained Leonardo da Vinci. But of course, if Freud sort of applied this idea to Zarathustra of Nietzsche, he also could have explained the behavior of Zarathustra in these terms. Also, you can psychoanalyze God Shiva, because he also sometimes abstains from carnal relations, but then somehow explodes in his anger and also immoderate like violence. But I think Indians know best all the details about their god Shiva and how he changes from, say, this hermit existence on Kailas Mount, and then suddenly he gets involved in some events, starts to dance, or starts to, well, interfere in some human activities, and always does it with a great energy and some violence also. So also this can be explained in terms of Freudian psychoanalysis. So you can psychoanalyze not only men but gods also, and religions. Thus is born the famous work of Freud, The Future of an Illusion, where he tries to psychoanalyze Christianity, the future of an illusion. Well, this was one of the late works of Freud, which was published in 1927. Well, this is how it goes with Freud. Just I gave only, he died in London in September 1939, perhaps of suicide, because he suffered from cancer of the mouth, I would say. Okay, now I think we have only 5 minutes, so we have to sum up. So we made great progress. I think we made some excursions into the 20th century. We started from genetics, and then followed this we followed the logic of the lecture of Max Planck, delivered in Berlin University, and spoke a lot about so-called scientific revolutions of the 20th century. First of all, relativity theory and quantum mechanics. Of course, we didn't cover all the details, and it is impossible, I think, to do that in 3 hours. But then we just discussed the, I think, very important sort of controversy that happened between Bohr and Einstein on determinism or indeterminism. And somehow logically, this was also connected with Freud and Spinoza, so relations. And also, I think a part is this evolutionary concept of the universe, which again, introduces us into this main also division of stationary and evolutionary. You see, this one division is determinism and versus indeterminism, and another is evolution versus stationary. Okay, so also, of course, we can discuss the guiding principles of evolution. So what started the evolution of the universe, whether we can find there some struggle for life between particles, or it is just peaceful evolution in Lamarckian or say sense. And I want to end with a citation, optimistic citation of Condorcet. Please, Marina, if you are still following us, produce this slide, maybe perhaps the last one with Condorcet. It's very just very provocative and interesting citation. No, Feynman will skip him. Yes, here. So this is like a prophecy. So there will come a time when people will be free. Then there will be no tyrants and no slaves, no stupid men, and no hypocrites could just master human, just people. And so this will be a happy time. So this was published in 1789, but this is a fourth edition of this Condorcet work. So the first edition was published in 1795. So we have anti-utopias like Zamyatin, Orwell, and Huxley, but we have also utopias. So the people, some people, Condorcet, for example, or Karl Marx or Auguste Comte, sort of promise us a happy future. Okay, so don't be too pessimistic. Schopenhauer is pessimist, but Leibniz is an optimist. So in scenarios of the future, we also have pessimistic scenarios and optimistic one. So Condorcet is optimistic, so I want to finish on an optimistic note. Thank you for listening to me, and please follow my lecture. The last lecture will be delivered on Thursday, and tomorrow we'll have a first exam. Okay, so now if there are no questions, we can say goodbye to each other. The exam will start at 9 o'clock, I think. Marina, is it okay?
Yes,
yes,
fine.
so, yes, 9 o'clock there will start an exam, and we'll see how it will go. But no, the link will be, the link is already in announcements. The link for the first exam, I think, is another link, not the same link as today.
And yes, it is the same link.
The same link. Okay.
Yep.
Okay, that's fine. That's just to start. We'll start the conference tomorrow at 9 o'clock. It will be a little bit easier for me because I will have to be silent and not sort of how to say spend so much energy. I will sublimate it somehow. Okay, so let's meet tomorrow at 9 o'clock because I think everybody are tired. Yes, no, I'm sorry. If you want, you can connect. If you want just to see how it goes, just to imagine yourself in the same situation, you can, of course, or if you have friends who are passing the exam and you want to somehow to, because the chat will be open and you can also put questions, or you are interested in the topics, or perhaps you know on which topics will people speak. So you can, of course, you are free to enter. But if you have other obligations, other duties, of course, you can stay at home and use your computer in another way. Okay, so it's up to you. Okay, so now I think we can thank Marina for her, I think, indispensable, or how to say, very important help, and we can end this conference. Okay, Marina, thank you very much.
Thank
You
you
are
too.
precious.
Thank you too.
Mhm.
Goodbye. Goodbye.
Goodbye. Goodbye. Till
Thank you,
tomorrow.
Professor. Goodbye.
Thank you, Professor. Goodbye.
Thank you.
Goodbye. Goodbye. Okay. Goodbye. Goodbye, everybody. So be happy.